I'm determined to learn geography. It seems so useful. It's just very difficult to use at times. It is helpful you understand this.
We can do anything, but you don't know how to do the anything.
No, honestly, that's pretty accurate.
That's what you have me to come up with mildly chaotic, silly analogies.
Okay. Let's start. Let's take pictures of you because so to know who is coming to classes. The normal. Say again.
I said you didn't dress up today.
It's, just if at the end of the semester we'll have arguments. Hey, you think I got 90, I got 88, but I should be promoted to A because I came to all the class and then I was highly participated. I said I don't remember you, and that will help me maybe quantify a bit. Okay, we are talking about yes.
Would it be possible to have an extension on homework 5?
Okay, homework 6 is out. Well, like right now, but sure, yeah. Yeah. Homework 5 is due today, but people want more time, which I guess is fine. Yes, yes, yes. That's just cut and paste. I didn't edit the date. Yeah. Uh, yes. The one that I just released just contains a bunch of questions. Most of them are on linear programming. One question does union of rectangles, where rectangles don't tend to be pseudodisks like this one, but in this case I'm saying it's rectangles for which the width is somewhere between 3 to 1. That would be one family, so you have a bunch of such rectangles. They might be of different sizes, but the height of all the blue ones, sorry, is the height of all the blue ones is 1, and the width is somewhere between 1 and 3. So they cannot be very narrow. They can start by being a square, and then you can pull it to the side, and then I called it horizontal rectangle. Or it can be a red rectangle, which have a height of somewhere between, age is between 1 and 3, but then the width is 1. So I could have be a bit more general about a statement, but that's close enough. So you have a bunch of rectangles. They all belongs to one of these sets. That is, the width, I can be a bit more general. The width is somewhere between 1 and 3, and the height is between 1 and 3. So definitely not pseudodisk to can create cross each other, but you need a bit more to play with them, and then you can prove something about that the reunion is linear. Okay, any questions about homework 5? If you are already there, sure, you'll get more time. But questions about it? No. Okay. So that's a topic that I also teach more or less in 445 with some variants. So I assume that some people have seen it. Okay. So we want to linear programming. That's a big problem. We want to design good diets. That's a sub-problem that we're going to study. So, yeah.
Sorry, real quick, for homework 5, question 2, it mentions that a line will cut the maximum number of lines. Does that just mean that it intersects as many as possible?
Yes. So, and of course, tell me whom do they intersect, to be precise. Let me double see what the question is. So you're giving a segment and axis parallel and suggest an algorithm that intersect here as many squares as possible. So, yeah. It's somehow tricky if you didn't get it. The reason that it's tricky is because a line, question 2 in the homework, a line can intersect a square, but I cannot tell you what of the edges that it will intersect. It might intersect, let's say, this and this, or might intersect this and this, or this and this. So there are a lot of options of how the line can intersect it. So that's why I thought that it's a bit more tricky. Yeah, because, yeah. Okay, the diet problem. That's how I'll tell you what is LP, and then I'll ask you in one of the homeworks to play with this app and just tell me that you understand the terminology, basically. I'll ask you to take a few snapshots, which is just it's nothing besides that you understood the terminology. So in the diet problem, we need to compute two values, x and y. These are the variables. That's the unknown x and y. And x will indicate how many bananas per day I'm going to consume. I'll think about it as a float number. 0.3 bananas is fine. And y will indicate the number of oranges, same deal. And the goal is to find a healthy diet. I'll tell you in a moment what is healthy. And it should be as cheap as possible. So just to remind you stuff about half planes. I can look at the half planes, all the points x and y, such that y is larger than x. So it's a region in the plane. There is a line that bounds, that's all the points in the blue region. And there is a line that bounds these half planes. That's a shared point with the opposite half planes of all the points that are y that is smaller or equal than x. If I'll take the line y is larger than minus x, y is larger than minus x, then the orientation of this line will go through 0, 0. If I'm going y is larger than minus x plus 3, then it's pretty much the same line, orientation of minus 45. It was just shifted by 3, right? So it's y intersect is 3. That's the line, and the half plane are all the points above this line. And in a moment, each such half plane will be some criteria about health. And if I want to satisfy more than one criteria, two criteria, I can ask what is the intersection of two such half plane region that is the intersection, which means it satisfies the points in the blue satisfies this criteria and also satisfies this criteria. Similarly, I can satisfy three criteria by taking points which are in first half planes, intersection with second, intersection with the third. Yeah, that's just point. Remind you, point is convex. We didn't talk about convexity for a bit. Point is convex if for any 2 points, A and B, look at all the segments between A and B, it's inside the shape. That's what makes the shape convex. And I'll remind you also that half planes is convex. Take 2 points that are above the line, then the whole segment is above the line, which implies that intersection of half planes is convex as well. No matter how many such half planes I'll take, it remains intersection. Now, intersection of 3 half planes will be convex. It might be bounded. It can also be the empty set, as we'll see shortly. If I'll take this half plane, now when I'm writing, we'll see a lot of half planes today. Half plane, I'll draw a line and I'll get some small tails, some ferry on one side of the half plane. That's a side of the half plane that I'm talking about, but where this little arrow points to. So here is one half plane, here is another one. So now the intersection is everything here in below, and here is a third one, all the points that are above the third line. So now it has empty intersection. Let's also talk about half planes using vector notation. I can think about the half plane by specifying a point P on the line, say. If I want to speak about the line, I can talk about the point P. I can talk about the vector n that is orthogonal to P. And now I want to speak about all the points x such that P vector, all the points x, it will be confusing. I'll try to be very careful about it. X with vector sign or bar above it means x and y, or x, y, and z. So, and x with no bar is just the point, one scalar, just a curve, x and y. Okay, so the point x, which is x and y, let's take now all the points x in the plane such that n times x equals n vector, the vector n, times p. So get familiar with this notation. All the points x in the world, that is pairs x and y, such that n dot product of x equals n, the vector n, dot product of p. Think about p as a vector. And I want to tell you that that's what a points need to do to satisfy it is to be on this line that I just created, that go through p, and its direction is orthogonal to the vector n. And that's quite easy to prove if we remember that dot product, if I have two vectors, u, v, such that u dot product v equals 0, but neither u nor v has 0 length, what does it tell me? You all know it. Angle between them, 90 degrees. Right? If and only if. As long as the length of every vector is more than 1, at least, either one of its components is more than 1. So look at all the points here. All the points x such that nx equals, let's shorten it, nx equals np. Np is, I don't care which one, but it must be a point on the line. So what are the points that satisfies this inequality, this equation? P by itself satisfied it. And if I have another point, P prime, on this line, I want to argue that if I have another point, P prime, on this line, then what do I know? That this is satisfied, meaning that np prime equals n times p. Fair enough? Because I said p prime satisfies this inequality. Actually, I start from the opposite direction. I said, assuming that p prime satisfies this equation, I want to convince you that p prime is also on the line. Because what are all the points on the line? It's all to be, the line is defined by the vector n, and the point p. So if np prime equals np, then np prime minus np, which is, because it's dot product, linear, equals n times p minus p prime. But we said that they are equal to each other, then it's 0. What did I study? that the vector n is orthogonal to the vector p prime minus p. And it's if and only if. Meaning that the vector that to go to p prime, I'm going in the direction that is orthogonal to the normal, meaning I'm on this line. And in 3D, it would be on this plane. In this 3D, everything is the same, except that n is a vector in 3D and p is a vector in 3D. And this will be the inequality of a plane. And to make it a half plane, to make this guy into a half plane, I'll write nx. Before that, I had equals np. But n is a vector all this time. It's a normal vector. That's a plane. To make it a half plane, I should make it large or equal. These are points on the line itself, as well as all the points on one side of the line. Think about it. If that's the direction of n, then the more I go in this direction, the larger this value is. Anything need clarification? Some of you saw it. I might be nasty about those times that you. Okay, just a slide that will be repeating the same thing, just in d dimension. V is a vector, u is another vector. Now I'm living in d dimension. D is a dimension in all these places. The dot product, u dot product v, refresh your memory, you are taking the first component of u multiplied by the first component of v multiplied by the first component of u, second by the second, third by third, sum them all up. That's a dot product. And of course, u times v equals v times u. U times v plus w is u plus v times u plus w. A unit, the length of the vector is just take v dot product v and take the square root. Why? Because of Pythagoras. When you look at on a vector xy, when I have a vector xy, that's v, then v dot product v is what? It's x squared plus y squared. And Pythagoras tells me that the length of this vector, the distance from 0, 0 until the end of the vector, is what? The x projection plus square plus the y projection square. That's a square of the length of this guy. And if I'll take the square root of this expression, then of course I'm just getting the length of this vector. The distance from the origin till the end of this vector. And I'm not going to this endless discussion about is vector is a point or a vector is a direction and a length. Sometimes it's this, sometimes it's this. Okay. Vector as opposed to scalar. Obviously, scalar is just a number. Vector is either a geometric creature or at least a list of numbers. Think about a vector in each case. Here is how I represent a line. Line are all the points x, such that v dot product x equals 0. That's one way. That's a line that goes through 0, 0. The point 0, 0 is on this line. And in general, if I'll change this line, but to say L times x equal v times x, then I'm just getting, so if I'm saying instead of v times x equals 0, I'll say v times x equals 1. I'm moving this line, but parallel to itself. If I'll ask v, the same vector v times x equal 2, it's this line over here. It's the red shifted by some amount, and if I'll increase it by some amount, it will move by the same amount. It's all linear. add the 3, change the 3 to 4, the line will move parallel to itself. But every time that you increment by 1, the line moves by 1 unit, or at least the same amount. Okay. Back to our diet problem. So I have a lot of constants that are the input to this problem. I have the constant I1 that says how many units of vitamin I have in a banana. I'll have multiple types of vitamin. I'll measure the health of the diet based on, do I get all my vitamins? That would be my only criteria for the health. Do I get all my vitamins or not? 1, 2, 3, 4. I equal 1, 2, 3, 4. And I need some input for this. My diet, by the way, will consist of only oranges and bananas. Nothing else. Only oranges and banana. I need it to be a healthy diet, for which I need to know, do I get all my vitamins? So AI, 1 is how many units of vitamin I do I have in a banana. AI, 2, how many units of vitamin I, the same I, do I have in an orange? Now, let's assume that I take 2 oranges and 3 bananas. And 3 bananas, and I'm asking how many units, just to see that we're in the same page, how many units of vitamin 1 do I get? If that's my diet consists of 2 bananas, 3 oranges, how many units of vitamin 1 do I get? A11 times 2, because it's A vitamin 1 for item 1, which is a banana, plus 3A1, 2. But that's a unit of A of I, vitamin 1, but in an orange, so the 2 refers to oranges. That's how many units of vitamin 1 do I get with this diet of only 2 oranges, 3 bananas outside. Vitamin 2, it will be A21 and A22 are the coefficients of how many units I get from oranges and banana of vitamin 2. AI vector is a 2-dimensional vector, and its parameters are AI1 and AI2. What now? X and Y are how many bananas, that's X, and how many oranges, that's Y, I'm going to consume per day. Do I know if these parameters, X and Y, are healthy for me? Let's check. Does that satisfy my vitamin 1 requirement? So A11, units of vitamin 1 in a banana, times X, plus Y times A12, and now I need another constant. So that we are going to have a lot of parameters as input, fixed constant. If it's B1 is how many units of vitamin 1 I need per day to consider healthy. B1 is how many units of vitamin 1 I need per day. I can get vitamin 1 from either oranges or bananas, doesn't matter. But the total sum should be at least B1. And that's just check for the criteria of vitamin 1. If I have N vitamins, then I have similar constants of how many units of vitamin N I have in oranges, same for banana, and I need to get N, part of the input. So B1 dot Bn are parts of input. And of course, what I will try to compute is what are the best x and y that I'm going to have. Shortly, I'll also have a price associated with each one of them. But at least the constraint so far that will tell me what x and y are legit is that for every one of these vectors ai, combination of ai1, ai2, ai times the vector x, which is what? ai1 times x plus ai2 times y, should be at least bi. Remind you again, ai1, ai2, bi are all constants. Input to my program, the only thing that I need to find is what is x and y. And this is going to be a linear programming in 2 dimensions. Why 2? Because that's a number of unknown that I'm going to have. Had I have also avocados in the game, then I had to decide about its quantity, which would make it a 3-dimensional linear programming. Okay, let's wait a second. With the cost, let's see how it looks. So here is my input. From vitamin 1, I need to get from vitamin 1, vitamin A, I have 7 units of vitamin 1 in a banana, 1 unit of vitamin 1 in an orange, and the x coordinate here will be the bananas. The y coordinate that I lost somehow is a number of oranges. So every point x and y here, every point x and y is a diet. Not necessarily a healthy one, but once I put the point x and y in the x, once I decided what is x and y, I can tell you, hey, it's you have a diet in mind. That's x, y, that is, what is this? 70 bananas per day, 50 oranges per day. That will be a potential diet. What is my first constraint? Saying that in the number of units of vitamin A, vitamin 1 in a banana is 7. Units of vitamin A in oranges is 1 unit in orange. And the requirement per day is at least 65 units of vitamin A. So what does it tell me about x and y? How do I know if this point x vector satisfies my condition for vitamin A or not? Well, look at this equation. The equation tells me 7 times x, number of bananas. 7 times x is how many units of vitamin A did you get from the bananas only. 1 times y is how many units of vitamin A you got from the oranges only. Sum them both up. It must be 65. At least 65, or else it's not a healthy diet. And that has a nice geometric interpretation. Look at this line. This line is 7x plus y equals 65. The line goes from minus infinity, so there are also points along this line that are probably not relevant. I don't know what is negative value, but at least in these values, what does it tell me about this part of this line? That if my diet xy is just on this line, then you will just barely get the minimum amount of vitamin A per day. Be anywhere to the left of this line, it's not a healthy diet. Be anywhere to the right of this line, we considered it a healthy diet as far as vitamin A is concerned. And for visualization reasons only, I decided that you are not consuming more than 80 bananas per day. So that's just for visualization. So if now I want to ask, where are all the diets for which I'm getting enough vitamin A, at least the bare minimum or anything larger than the bare minimum, it's what? It's a half plane. Remember, on the line, I just get bare minimum of vitamin A. Anywhere to the right of this line, you're getting the minimum or more than the minimum. So vitamin A-wise, this striped region is healthy. You got at least enough vitamin A. And I just chopped it an 80-80 for visualization. But it goes to infinity. So that was for vitamin A. Go to the same table, I have some constraints that refers to vitamin B. From vitamin B in an orange, I have 4 units. In a banana, I have 2 units. Maybe it's the other way around. And I need at least 70 units to make it healthy. That's for vitamin B. That's this line. And for a diet, XY, and that's a point that you might lose me. Every point XY in the plane corresponds to a diet, at least in the positive X, positive Y, corresponds to a diet. I'm just trying to find what are the region of all the healthy diets. So I need to be to the right of this line to get enough vitamin B. So here are the region of all the points that you are getting enough vitamin B. But you need to get vitamin A and vitamin B. Here is a region of vitamin B, vitamin A, remember? Here is a region of vitamin B, and I need to be in the intersections of these 2 regions because I need to satisfy both constraints, enough vitamin A, enough vitamin B. Similarly, I have constraints for vitamin C and D. 5x plus 14y should be 200. You need at least 200 units of vitamin C, and that's how many units there are in orange and banana. Similarly for vitamin D, so these are 2 lines. And that's the intersection of these 2 half planes. And where are all the healthy diets? All the healthy diets are just the intersections. Healthy diets are just the intersections of the 4 half planes defined for all the 4 types of vitamins. So if we are ignoring that, I cut it in 80, that's the region that is what? Intersection of half planes is a polygon. You can compute it. And every point here satisfies everything that I need health-wise. Okay. Let's put the diet outside, and now let's look at the cost function. The cost function is another 2 parameters that somebody gave me. What is the current cost of an orange? What is the current cost of a banana? Now, I want a healthy diet, but I don't know for the healthy diet how much will it cost me. So what do? I play. I'll assume that I'm willing to spend $80 for the diet. Assume that I'm willing to spend $80 for the diet. Where are all the diets that I can reach with exactly $87? Well, if an orange costs this and a banana costs this, then 1.6 times x plus 2.8 times y should equal to 87. Right? Every point here costs you exactly 87. It's a diet that costs you exactly 87. Of course, that depends on the current prices of banana and orange. Change the cost of one of them, and of course, this line changes. If I make banana cheaper, then you can buy more bananas for the same cost. Makes sense. And now, finally, I have the linear programming algorithm, at least the first one. Because now I can reduce my budget again to 0. Look at the polygon of all the healthy diets. Compute maybe the polygon of all the healthy diets, and slowly, slowly increase the budget. Remember, this line are diets that you can afford. This polygon are diets that are healthy. With a budget of whatever this is, budget of $21, there is no healthy diet that I can afford. But I can slowly, slowly increase my daily budget until I finally hit one of the vertices. And this vertex, notice that when I'm changing the budget, what happened to my equation? We said 16x plus 2.7y equals to my daily budget. If I'm changing my daily budget, the orientation of this line doesn't change. The normal is just a cost vector that you'll see soon. It's just these two numbers from the numbers, the two costs. That's a vector orthogonal to it. If I'm changing the daily budget, what happens to this line? What happened to my stick? Changing the daily budget, this line moves parallel to itself, very important, always orthogonal to the cost vector. And I'm asking what is the first moment that I hit the polygon, that I hit a healthy diet. And that's cool because this is a polygon. It has vertices. So we already proved a pretty important result. The healthy diet, when you're after the cheapest healthy diet, you don't need to check each and every point in the feasible region. You don't even need to check every point on an edge. The cheapest healthy diet must be a vertex. It's the first vertex that you'll hit when you're moving this line in the right direction. Make sense? So the optimum must be obtained in a vertex. And that's why convex programming is so much, much easier than non-convex programming. You have a single local maxima or minima, which is also the global maxima, optimum, minimum, maximum. And if it looks locally like it's locally the cheapest, it's also globally the cheapest. Yes? So,
Like for the vertices, like take all the vertices, then calculate the cost based on the vertices. Would that be quicker?
that will be an algorithm. We will start by doing it, and exactly then we'll see a faster algorithm, because that doesn't scale great with the dimension. Nothing scales well with the dimension, but that's worse than others. Okay. I don't think that I asked you my cat question. I asked in this course? Not yet. Yeah. Okay. So did I teach you linear programming in this course? Not yet. Because I also did it in 545 and in 445. So people might have seen it. We are going definitely deeper than in the basic. Yeah.
So back to the previous example with the diet, I'm kind of wondering if we have our cost vector is normal to the line of affordable configurations, why can't we just check when the cost vector intersects our half lanes?
I can do it slowly. It's not a cost vector. It's a line orthogonal to it, but it's not a fun algorithm to do it. Instead, I'll compute, at least naively, I'll compute for every vertex. What I did in all this gymnastics is to convince you that I don't need to check anything besides the vertices. What I'll convince you next is that I don't even need to compute all the vertices. going through this question very, very quickly, what we want to ask here, I put a metal band around the Earth. I move these metal bands by just a bit, adding 6 feet, asking, can a cat move underneath it or not? And why do I ask about it? Because you see that the radius versus the radius versus diameter is a linear function. And what's nice about linear function is that if I have some delta x somewhere between x0 and x1 I keep delta x fixed, then delta y will stay fixed as well, no matter what is x. Why is relevant to my little puzzle? Because the fact that it's Earth is irrelevant. It can be a tennis ball, and you'll still get the same delta y before and after you extend it. So this about 1 foot that you have in the gap doesn't matter at all in the Earth. But it's definitely useful for this whole chapter about linear programming, because all our cost functions and all our constraints will be linear, which means, for example, that back to our budget, if I'm moving the budget by some amount, the gap that my vector jump, the gap between this line versus this line versus this line, if the cost change linearly, then this vector moves linearly. The gaps between steps are the same. That's going to be actually very useful for us. Okay, linear programming, the geometry. In 2D, ax plus ay larger or equal than b, or ax plus ay smaller or equal than b, defines a half plane. You have several such half planes, and and the feasible region are all the points in the intersection of all the constraints. Constraints were the vitamins, nothing to do with the cost function. Of course, I can have a different linear programming question that asks, can I find any healthy diet of cost less than $100? And then I have a bunch of half planes, and now I ask, do there either an intersection or not? So it's not an optimization, but I'll still use the same algorithm to ask, is a feasible region empty or not? So that I can make it into an LP with one more constraint. But at the moment, these are only the vitamins. Look at their intersections. The intersection, it has a name, that's a feasible region. And the feasible region is convex. It's all the points that I'm willing to accept as a solution before I look at the cost itself. Okay, intersection of half planes. And I mentioned it. If I have a line in the plane, then one side of the line is half plane. If I have a plane in 3D, then one side of this plane is half space. And in hyperspace with 4 more dimensions, I have a hyperplane, but one side of the hyperplane is half space as well. We don't go through half hyperspace. We don't say it. It's still half space even in higher dimension. So, theorem, any bounded linear programming that is feasible, there is at least one point that is feasible, has a solution, and this solution is a vertex of the feasible region. Right. Here is my cost vector. It means that's the steepest descent. If I'm going in this direction, my cost changes in the maximum speed, increase or decrease. So think about this as gravity, or the wind pushes me. What is the maximum point in this direction in the feasible region? It must be a vertex. Don't confuse, I'm not saying that it's only at a vertex. It could be that I have 2 vertices with the same cost function. But it must be a vertex. Proof. Let's follow C and let's assume that we hit an edge. I saw that based on the cat ideal. I saw that going in this direction makes my cost cheaper, say. Then if I follow this edge, what's my option? I hit this edge and going from the heating point to both direction or to any direction in higher dimension, keep the cost exactly the same. That's one option. And then in 2D, I'll just go to one direction arbitrarily until I hit a vertex. So that's a vertex that has the same cost function as here. Or here is my cost vector. I hit, that's where I hit it, and I look to the right, look to the left. One direction is better, and because of the cat linear idea, if I'll keep walking along this edge in this direction, if going by dx improved by dy, then keep on going. It will make your cost better and better, again, until you hit a vertex. So the difference between the cases is that here I am saying left or right, versus the first case that I said it doesn't matter left or right, they are all equally good. So either that I have an edge in 2D that all this edge is the optimum, or that it's only a single vertex. But it's always the case that one of the vertices has the optimum value. That is, we don't need to check anything besides the vertices. The generate case, the linear, the feasible region, the intersection of the three half plane might be empty. We saw it before, three half planes that with no points at common. I cannot do it with two, but I can make it with three. I can do it with two, but then they need to be parallel to each other. It could be unbounded. Unbounded doesn't mean that my cost is, that my solution is infinity. But it could be that it's unbounded to this direction, so if I'm looking for the lowest point, I'll get to this point. If I'm going to the highest point, I can go to infinity. Or it can be that I'm looking for the lowest point, but it's not unique. Okay, let's play a bit. So in the 2D, I just have bananas and oranges. What I can do is to construct the feasible region explicitly, given the half planes, and then check each vertex independently. And this could be done in n cube, and how do you do it in n log n? Gram-scan of. I have the half planes. Gram-scan is a good answer, but I have as an input half planes. No, Gram-scan is a good answer, but Gram-scan doesn't take half planes as input, doesn't take lines as input. Gram-scan works on points. I want to compute the intersections of all these half planes, and I want to use Gram-scan. It's a great idea, but these are lines. These are not points.
You find all the intersections of
I want to find the intersections. That's, go to the dual. What is this portion? Think about it. It's the lower envelope of all the half planes that points downward. But I think about this polygon as the intersections of three half planes that points look downward, contain the points y equals minus infinity, intersected with, say, two half planes that looks to upward. Contains the point x equals 0, y equals infinity. That's a polygon that I want to compute. What do? I make every such point into a line, every such line into a point, and compute the convex hull via a Gram-scan. That would be one n log n. And if you think about the vertices here are just corresponding to edges of the convex hull. A vertex here is a line that contains an edge of the convex hull. So that would be one algorithm. Another one would be compute pairs and then 4 tuples and then 8 tuples using recursive line sweep. It's another algorithm, and it will also work in n log n. N log square n is what we talked about without any tricks, but you can get rid of log n because you're recycling the sorting. And there are more, but it's all n log n. So in 2D, if you're willing to spend n log n, it's not a very interesting problem. N log n is fine. Take all the half planes, compute all their vertices. By the way, it might be that the half planes don't have any point in common, so you're reporting no feasible region. But if they have a point in common, then you're happy, and you are saying, yeah. And then you're computing for each one. You're given the cost function, the cost of banana cost per oranges, compute it for every vertex. We just proved that you don't need to check anything but the vertices. So one of the vertices will be the optimum, and voila, you're done. And by the way, you're also noticing if the solution is unbounded. Maybe you don't have any vertex in the correct direction. This polygon might be open. 2D, no problems. I throw avocados into the game with bananas and oranges. Now I have 3 dimensions. Now the dualization trick takes more work computing convex hull in 3D. It takes more work computing lower envelope and upper envelope. You can still get away with all of it, but you can see that just the line sweep starts to needs some patching. But it's still, if I have n half planes in 2D, what is the complexity of the polygon, the intersection? That's an easy question. N half planes, what is the complexity of their polygon, which is their intersection? At most n, every half planes will contribute. At most one edge, I might have some redundant half planes that don't really contribute anything to the intersection, don't have an edge. So at its most n, because every edge lies in one place. What happened in 3D? How many vertices, edges do I have? Takes a moment to think. 3D, think about the polytope that is the intersection of n half spaces in 3D. What is its complexity and why? So we will use this notation quite a lot. H1 is a half space. L1 is a boundary. It is a plane that defines it. H1 is a half plane, and L1 is a line that defines it. So now the whiteboard is H1. And tell me, how do I compute the face of the feasible region, which is on H1? I assume that H1 is not redundant. It contributes something to the feasible region. How do I compute what is the face on it? Yeah.
So since the whiteboard is a rectangle, I want to say it's going to be n squared because the area of a rectangle is length times width.
The whiteboard is infinite. Yeah, all the way to. But I have one of the other half planes. How does it look like? It's a plane. It's a plane that cuts the half board in some shape, not parallel to the half plane. I said no parallel planes. It's a plane that cuts it. So what is a face when we look at the polytopes that is the intersection? So you are all on this side of the half plane. So you are satisfied and all in the good place of vitamin A. But I have other vitamins. Yeah. Two planes intersect on a line. So this line is with or L1, sorry, intersection with L2. What is L2? It's a plane that is a boundary of H2. That's this line. Here is L1 again, the whiteboard, intersection with L3. Another one, another one, another one, another one. And this is in the feasible region. That's one face of the polytope. Convex, nice, that's one face. Is a polytope convex? Yes, because it's intersection of half spaces. Every half space is convex. How many things, edges, vertices, does it have? Edges, faces, vertices. Let's start with faces. How many faces are there in the feasible region in 3D? N. Every half planes contribute one polygon to this polytope. Everybody understand what I'm speaking about, this polytope? That's my polytope. It's intersection of 6 half planes. Okay, so every point here satisfies all the 6 vitamins requirements. So number of faces is n. Number of vertices, edges. Good final question. Bear with me a second. Looking for a piece of a box that I can show my students. Imagine. So you're looking into the polytope. I didn't want to open the box. So you're looking into the polytope, one face, one face. Right here, that's the one that includes me, another face, another face. There are n faces we obtain, yeah? About, more or less, because? Let's say I just cut, I chopped it in the middle. So look at it, one face, and it's convex. Come on, one word that I'm looking for. Why? One edge, one face. It's just a map, right? I mean, the fact that I didn't stretch it to be on the real geometric plane doesn't change the topology. Each face has the same neighbors as before. Each edge has the same neighbor. So I can just treat it as a planar map when I open it. I can place my fingers. It's an orange algorithm. It says, place your finger into one of the faces, pull it to the side like an orange. It will all open up, and the edges might become non-linear. They can be elastic, but still every face will have the same faces as neighbors in this rubber box, right? So I can still use Euler formula. So if one of them is linear, then if number of edges is linear, the number of faces, number of vertices are all linear. So everything is great in 3D. It will be a slower algorithm. It will be in constant, it would be much less fun. But you can do it in 3D. Going up the dimension, curse of dimensionality. Always suffer it, but really suffering it here. If I have D types of food, then in my feasible region, that's possibly the number of vertices that I have. So n is the number of constraints, number of vitamins, to the power of d half. Not practical. I am not going to build all of it in any reasonable time. What do I do instead? Option 1, use a simplex algorithm, which is kind of steepest descent. It says, start from a vertex in this polytope, and now pick an edge for which moving along this edge, let's say, pick this vertex, moving along this edge, I'm trying to go as low as possible. My cost function C points downward. Start from this vertex, follow an edge that will take you downward until you hit a half plane, a vertex. Now it generates another edge that you can improve along this edge, and now you get to a local minima. In general, the simplex algorithm might need to replace a lot of such vertices, and it could have exponential running time in some very, very rare cases. But usually simplex is what you are using, and it usually runs extremely fast. No matter how many constraints you have, no matter in which direction, it could be seriously enormous. And it will run very fast, and you'll find many implementation of it. Cplex is a common library called Cplex. Library is at IBM funded Cplex. And you can find here the simplex algorithm, including some IRP algorithms that we'll talk about later in the course. Yeah. Not normally. Simplex is, well, it's a class of heuristics, but each one is deterministic. We didn't add stochastically here. And again, it could be exponential, but in a very rare cases. It's actually proven that if I start from from a case that it's exponential, and I just introduce epsilon noise, just perturb them a bit, then with very high probability, the new polytopes that I'll get will be polynomial. So simplex is one such case. That's just a diet case, just a notation. If we have more types of food, again using vector notation, AI is a vector, X is a vector, how many bananas, oranges, avocado, yada yada. Food of types D. What do I need? That for each such constraints, AI vector times X should be at least larger or equal, sorry, typo, BI. It's not B1, it's BI for every type of vitamin I. That would be my constraints. And I also given the C vector, the cost vector, and I'm trying to minimize C dot product X subject to AI times X is larger or equal than BI. I mean the right side of the half plane. By the way, here you see it with larger or equal than BI. If you want to say I'm not getting more than 80 units of vitamin 3, how do you do it? Oh, my combination of vitamin 3 is not more than 80%, then it's not larger or equal, then you multiply both sides by -1, and then now it's becoming smaller or equal. The AI will change, right? That's how you get it from above. So that's general linear programming. And sometimes it's actually very convenient to write it using matrix multiplication. So I'll create a matrix A. What is a matrix A? Every row of the matrix A is one of the AI. Every row of the matrix A is one of the AI. X will be a column vector, and A matrix dot product X should be larger or equal than B. B is now a vector. That is the first row of A times X should be larger than the first component of B. B is a vector, so the first component, second component, and so on. And what do I minimize? The linear cost function, C times X. So that's general linear programming. And slight part of the course will be how do I express other problems as linear programming problems. And that's very useful because it's a huge tool. Then you can use either LP, or you can, I'm going back a bit, you can get many huge class of problem, including many NP hard problem that you'll get by writing it as an LP, except that I'll ask some of the variables to be integers, like 0 or 1. If I want to pick some subsets, like guards in a polygon, I can say here is a set of guards that I can pick from, and out of them, each guard is either picked or not picked. And I have constraints that are linear, like every point need to be visible by at least one guard. So that's about the LP. And that's how you called it from MATLAB. I think that and you can find it in other languages as well by just calling linear prog with just giving the matrix A, the vector B, the cost function F, and you'll get, as a result, the vector X. And it's up to you to understand what X, how X relates to the original problem. So you can have it as AX equal to B, other parameters that you are expecting AX to be equal to B, or small or equal, or large or equal, and lower bound and upper bound, etc., etc. So that's all about giving you artillery for more problems that you might see in your life that we are not discussing. And that's all, and max flow, by the way, is another problem that you can express as linear programming in much higher dimension. And it's nice that LP can solve it, and it can solve it in much more general terms than what Ford Falkerson or Edmond Scarp can solve it. You can throw on it many other constraints and it will work. Not in this course, so I'm skipping it up. Back to the simplex algorithm, just said, it's kind of steepest descent, but only work on edges of the polytope. And we want to have a faster algorithm in small dimensions. Small dimension would be 3, 4, 5, 6. Then even in 2 dimensions, it would be nice not to go to the n log n, but to a linear time algorithm. And if I want linear time algorithms, then take my word, a convex programmer, convex hull, if you remember, we cannot compute in time better than n log n. We said that the feasible region is a dual of the convex hull, so we cannot compute all the vertices in n log n. But I still want linear time algorithm, at least the expected linear is going to be randomized. How am I going to obtain it? I'm not going to compute all the vertices. I'm somehow going to only pick subset of vertices and only important one. Let's progress a bit. I want to talk about one-dimensional linear programming. So I have a line, and I have constraints alpha 1 dot 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 alpha n, beta 1 dot 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 beta n. Now they're all scalars. They are nothing. And I want to find a value x such that x is larger than each alpha I. Remember, x is not a vector, it's a scalar, just one parameter. Alpha I is also just a scalar. X is larger than each alpha I, and at the same time, x is smaller than each beta I. And I want the minimum x. And I want to do it in linear time. How should I do it? Easy. Sorry?
Is it binary search?
Even simpler. Kind of, yeah. It's
Find like the greatest AI and then the smallest BI.
out of all the AIs, I'm looking for X that is larger than all the AI, all the alpha i's, sorry. So every alpha I, think about it as it should a raise to the right, or it is a opening of a parenthesis. Every beta j is a closure of parentheses. Out of all the, and I'm looking for X that is to the right of all the alpha i's, but to the left of all the beta j. So from the alpha I, what is the only parameter that I care for? The maximum value of the alpha I. So find the maximum alpha I. Among the beta j, the only one that matters is the leftmost one, the minimum of the beta j. And now the feasible region, again in 1D, are all the points, sorry, feasible region will be all the points between the maximum and the minimum. And by the way, it can be that, so find maximum of alpha I, minimum of beta j, and it can definitely be that if I want the minimum X, it would be this point, linear, but it can also be that alpha I is actually j, which will tell me that at least for this problem, there is no solution. No solution on this line, so based on the relationship of the max and the mean of each set correspondingly. So next class, we will see a pretty ingenious algorithm, made quite a splash because it was problems that many people thought before, of how do I solve linear programming in linear time, at least expected linear time, and that will work first in 2 dimensions, and then we'll go up the dimension. It's going to be quite cool. Okay, thanks.